So in this video we're going to talk about probabilistic logic, or how to use the Bayes theorem to think about the Bayes rate problem. I've already talked about this during the second lecture, but I think some extra exercise wouldn't hurt, and you can use this as a reference for studying for the exam. Also, it ties together the second and the third lecture in an excellent way, I hope. And finally, but most importantly, the people who have to do a presentation during the tutorial on Friday, they can prepare themselves with some extra instruction on how to think about the most important points from the article. So I think it suffices to focus for the presentation on the first few pages of the article, which I'm going to discuss here. So there are a couple of points which you should take from the article, in which Griffin and all first discuss. We'll give another couple of examples of why people aren't very good in calculating probabilities. So as they indicate here, a lot of people are surprised about the birth order of girl, boy, girl, boy, girl, boy, born from the same mother. In that order would be very unlikely, but if you're well versed in probability theory, you will know that every order would be just as probable as this one. But people fail to notice that, and that is why these kind of stories sell newspaper articles. So to give another couple of examples of why people aren't very good in calculating probability, and why their judgments or their preferences will or will not show coherence and calibration. I'm not going to explain that here, so make sure you read up on this in the article, or make sure your presenter will inform you on this on Friday. Also, something is mentioned here about the rational model, which I've already discussed with you, so it's a great way to check for yourself if you understand everything. At the exclamation mark, a point is made, which I will get back to later, either in another video or during the next lecture. So what we're going to talk about is the main point here, in which they indicate that a rational thinker calculates the odds. For example, the odds of winning the lottery, or the odds of drawing a blue marble from a container with containing 30 blue marbles and 20 red marbles. You know the exercises from mathematics in high school, which you can calculate during using variations of this theorem. So seeing as you might be a bit baffled by this formula, and you might not be, because you talked about it in high school, I'm going to discuss it with you here, and I'm going to discuss with you what the implications are of this model for rational thinking. So we're going to do this using a story in which Mr. Jones, a hypothetical person, a typical thin man, is going to who always uses the mathematics right and always calculates the right odds for making all his decisions. We're going to see how Mr. Jones, this fictitious person because he doesn't exist in reality, a person who can tell us all the proper odds for making all our decisions, we're going to see why it's difficult to make the same calculations which Mr. Jones makes here in his head. So during the lecture, second lecture, I gave you the example of the book by Richard St. John's, in which he, implicitly claims that because a lot of successful people have 8 traits in common, if you strive towards also attaining those traits depicted here, you will be great as well. And I've told you that this would sell a lot of books, presumably, or generate a lot of clicks on his YouTube video in which he explains this as well. Because people think, well, this is fantastic, let's do a little dance, because, well, all the great people which Richard St. John's had collected in one room all have these 8 traits. And this makes people happy because they think, if I read up on those traits and I'll make sure I have those traits, I will be great as well. So they confuse two probabilities, namely the probability of having these 8 traits when we know you're great. So given that you're great, how big is the probability that you have those 8 traits? Well, 100%. But it isn't the same as the probability of being great given that you have those 8 traits, which is the only thing you can make sure, or the only thing you can strive towards after reading that book. So that confusion in probabilities is why people make this error. In some situations it's difficult to see why you can't inverse those probabilities. In other situations, like in a Sharknado example, it's very obvious. So if I ask you what's the probability that you've been eaten by a flying shark given that you know that you've died, you'll say, well, that is very low, or the probability is very low. And if I ask you what's the probability that you'll die given that you've been eaten by a flying shark, you'll say the probability. So this piece of Sharknado wisdom is obvious because in a different example you see that those probabilities aren't the same. But still, in a lot of situations, people fail to see that. And we're going to analyze the probability. We're going to use Bayes' theorem, or the formula for calculating conditional probabilities in this example, for calculating what the odds are of being great given that you have these 8 traits. So we can be a bit more specific about the difference in those odds. So we already know that we have to use this specific formula, which indicates that the chance of Q given P equals the chance of P given Q times the chance of Q divided by the chance of P, or the probability of P, which we can translate in this example to the probability of being great given that you have those 8 traits, which is what we'd like to know, what interests us in buying this book, or drives our interest in buying this book. And we can calculate, in principle, by the probability of having those 8 traits, given that you're great, which we know, which is 100%, times the probability of being great divided by the probability of having those 8 traits. Of course, it's very difficult in a lot of situations to know what these probabilities are, which is one of the reasons why we're not well calibrated in making probabilistic judgments. And there's a lot of controversy about if we could use this formula at all in calibrating and updating our probabilities, or our degrees of belief, if you will. In some cases it's not controversial. For example, in frequentist cases, like in the example of drawing marbles from a vase, or examples relating to in which the proportion of cases in a population are known, like, for example, the prevalence of a disease in a larger population. But in more specific personal examples in which you calculate the degree of belief, it's more controversial whether you can use this formula at all. But bear with me, if you use it in this example, we're going to assume that we know these probabilities, so we can calculate this probability. So we know if we translate this formula, which we filled in here, into words, we can see that in red is indicated the proportion of great people who have these traits, which we know, which is 100%, which sells the book, times the Bayes rate, which is why errors in this department are called the Bayes rate neglect or Bayes rate error, because people fail to account for this piece of information, which is the point of this exercise. So it's indicated in blue, and the Bayes rate in this case is the proportion of people who are great, or the a priori chance of being great when you're born. So given that you draw at random one person from the population of all persons, what is the chance that that is a great person, given that you further have no information about that person? And in brown is indicated, or encircled in brown, is the probability or the proportion of people who have those traits. I wanted to write something else specifically here, but just assume with me that this indicates the proportion of people who have those 8 traits in the population. So if you draw again at random a person from the population, what is the probability that that person has those 8 traits? So if we have that information, we can calculate the probability that we'd like to know. So let's assume for this example that we know this. We know that this chance equals 1.0. We know that the probability, so the a priori chance of being great, call me a pessimist, are not that high, so 5% chance. And we assume for this example that the probability of having those 8 traits is very high because, well, those traits are very general, so most people would indicate that they possess them. So we can calculate it like Mr. Jones, the mathematically upright citizen, does right here. He would calculate for us by filling in the formula with those probabilities. But a lot of people have some difficulty in making this calculation, so it helps perhaps to translate those more abstract probabilities to concrete frequency examples. So how we do that is with using a frequency tree in which we start off with a hypothetical population of 1,000 persons, just 1,000 for easy calculations, and we apply the base rate to them. So we know nothing about this population except for that 5% will be successful and 95% will be unsuccessful, which is indicated here. From the unsuccessful persons, we assume for this example, bear with me, that 80% will still have those 8 traits. As I said, a lot of persons will have those general traits. And from the unsuccessful persons, the remainder will not have those traits. From the successful persons, we know all of them will have those 8 traits. So those are all 50 people, and the rest, well, there is no rest. So when we know these specific numbers, it's more intuitive to calculate the odds of being successful given that you have those traits, because it's just a proportion of people who turn out to be successful and have those traits from all the people in total who have these traits. So those are indicated here and here. So we want to know, we calculate what are the odds that you're one of these people from the total pool of these plus these people. And if you calculate that, it turns out to be a 6% probability, which is not that much higher than the base rate probability. So in our example, which is fictitious of course, the chance of being great given that you have those 8 traits is not much bigger than when you know nothing about a random person in the population. So I hear you wondering, what's the point of all this? Well, I'm going to tell you right now. What is interesting is that this is a very rational way of thinking about, well, human thought and human decision making, which is not that accurate actually, because if we like to know, well, we used to assume that people were rational people and they calculated odds or they calibrated their beliefs using logical or probabilistically valid or probabilistically correct rules, like Bayes, who is indicated here, would like us to do. Bear with me. But the whole point of the next lecture is talking about what we actually do, because we have just seen we failed to make this calculation, we failed to make this calculation, but we're probably doing something else. The question is whether we are bounded rationals, so we try to be rational, but we're bounded by environmental constraints. So lack of resources because you're tired all the time, or you're distracted, or you have to make a lot of decisions, makes you less able to apply your rational thinking, but you're still, in essence, you're a rational thinker, only in a limited capacity because of limited resources. So you're bounded rationalist, if you will. Your rationality is bounded. Or do we do something else completely? Are we not calculating probabilities at all? And do we, well, think about the possibility of certain outcomes and the probability of certain valued outcomes occurring in a completely different way, perhaps using heuristics, which is exactly what we're going to talk about on Friday. And that's it. You know all you need to know before entering the lecture hall for lecture 3 and preparing your presentation or your tutorial with ease, yes, and with pleasure, of course. But there's one thing, additional thing I'd like to point out. In the article, they give this version of Bayes' theorem, which is indicated here. Well, you can just see it, which it actually is, as a different version of this formula. In this form, it's more easier to compare or to calculate the odds of one hypothesis being more likely than the other, given a certain datum or certain data from your research, which is how Bayesian statisticians use it, but that use is still controversial. So if you see this formula in the article, just assume that it says this, which we just discussed. Okay, good luck with the rest of the article.